Welcome to the second part of elementary counting techniques. So I start from where I left. In the last lecture we have seen that the total number of combinations of n objects to form a collection of R objects with repetition. And at the same time, if I talk about this linear equation, then the number of solutions in non-negative integer values of x1, x2 up to xn, they add up to R, once again a positive integer, non-negative integer maybe. So we have seen that in both the cases, the count is n plus R minus 1 is R, or n plus R minus 1 choose n minus 1. Let us see a couple of applications of this result. The first one is about a program. I also introduced this program in the first introductory lecture. Unfortunately, there was a mistake. I will correct this mistake today. So consider this code snippet. Okay, let us work for a general n. In terms of n, what is the number of times hello is printed? Maybe in the first lecture, I have taken a specific value of n like 100. But we can anyway work for arbitrary value of n, and the answer will come to be a function of n. So, how many times? That is the combinatorial question. Okay. So we choose any three numbers u, v, and w from 1 to up to 20. Choose this. With repetition. Okay. And let us suppose that u, v, and w satisfy this. Now, I can sort them and call them u, v, w in that sense, in that sequence. Now, if I assign the value u to k, v to j, and w to I, then for every such choice of u, v, w, hello is printed once. So here I is the largest one, j is the next smaller one, k is the next smaller one. So, in the last class I have written I less than equal to j less than equal to k. It should be k less than equal to j less than equal to I. So for any choice of three integers from this set, satisfying this, without loss of generality we can assume that they are sorted. And if I assign k, j and I in this manner, then print this hello is printed once for this choice of u, v, w. And then if I use that formula, There are 3 elements that are chosen and the total population is of size 20. Sorry, this is n. There are n elements. So, it's not n equal to 20. In the book it is given it's 20, that's why I made a mistake. So, you are choosing anything between 1 through n. Okay. So, you are choosing 3 elements from population of size n. So, this should be n plus 2, choose 3. Okay. So, that is the general formula. And using this result on combination with repetitions, we can easily derive this formula. Of course, you can derive the same formula in a very hard way by exactly counting. So, for each I, j goes from 1 to I. So, it's a kind of triple sum, something like this. Of 1, I ranging from 1 to n, j ranging from 1 to I, k ranging from 1 to j. Okay. Yeah. So, this I can write this way, eventually unfold this, j equal to 1 to I and k equal to 1 to j, 1. So, that is once it is printed for each value of I, j, k. So, how many? J. And this will be I equal to 1 to n. Now, this is the sum of j from 1 to I, and we know that this formula is I plus 1 by 2. And then if I make a sum of this thing, it will eventually come to the same formula. Okay. But this involves a lot of algebraic manipulations, particularly the last sum is not going to be very difficult, but using this combinatorial argument, we can easily derive the formula. Okay. In a much simpler fashion, instead of going the hard way, the computationally or calculatively intensive way. Okay. Anyway, so this is a simple application. Let us look at something a bit more intriguing. This is another example. This deals with what is called partitioning of positive integers. Now, this partitioning deals with in how many ways you can write a given positive integer n as a sum of positive integers. Okay. So, number of ways of writing n as a sum of positive integers. So, illustrate this by an example. Take n equal to 4. 4 can be written as just like 4. This is a one-fold sum. We can write it also as 1 plus 3 or 3 plus 1 or 2 plus 2. So, 4 written as a sum of only one element, one summand. 4 written as a sum of two summands. Then we also have 4 written as sorry, 2 plus 1 plus 1 should be. So, 4 is written as a sum of 3 summands. Finally, there is 1 plus 1 plus 1 plus 1. 4 written as a summand, the sum of 4 summands. So, how many possibilities? 1, 2, 3, 4, 5, 6, 7, 8. Okay, I hope I am not missing anything. It should be fine. Looks fine. Okay. So here I am talking about ordered sums, because 1 plus 3 and 3 plus 1, the summands are essentially the same. But if I just, if I just permute this summands, I say that this is a different way of writing 4. And if you do not consider these and these as different, then this is an unordered sums we are talking about. Because these, they are all essentially the same up to permutation by the summands, permutation of the summands. So ordered, so this is 8 possibilities, ordered. And if I talk about unordered, this is 1, this is 2, this is 3, these are same, 1, 2, 3, 4 and 5. Okay. This quantity for a general n is denoted by Pn. It's actually difficult to arrive at formulas for P of n, closed form formulas. In fact, no closed form formula of P of n is known. However, if you consider ordered ways of writing 4 as positive summand, then there exists a very neat formula. And it is that formula that we will now derive. Okay. And there we will use that x1 plus x2 plus blah 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 equal to something. Okay. So suppose let's say n written as a sum of k summands. Okay. And written as a sum of k summands. What are the allowed values of k? 0 summands, that is not allowed. 1, 2, 3, up to n summands. These are possibilities, right? 0 is not allowed. If n is positive, then I cannot write it as an empty sum. Empty sum is always 0. So 0 cannot be equal to n, given that n is positive. Okay. So written as a sum of k summands. Let us call these summands x1, x2 up to xk. This equals n, right? Now, since x1, x2 are positive summands, I have to use this. And immediately the formula that I have given at the beginning of today's class, this lecture, does not apply. Okay. But if I use this substitution, yi equal to xi minus 1, then this equation reduces to y1 plus y2 up to yk equal to n minus k. Since xi is greater than equal to 1, yi is greater than equal to 0. So we are now in a setting where we can directly apply that formula. Okay. So, number of ways of writing or number of solutions of y1, y2 up to yk is now therefore by that formula. This is, in this case, n is k, r is this, minus 1, and I choose R here, n minus k. Right? The same formula, this notation is a little bit mixed up. So, earlier I used n here, now it is k. So, k, and it was r here, so r I keep here, n plus r minus 1, choose r. With this new notations, it's this. And what is this? n minus 1. This k and this minus k cancel. N minus k. I can write it as n minus 1, k minus 1. Right? N minus 1 minus n. Yeah. K minus. Now k can assign any, k can take any of these values 1, 2, 3 up to n. And therefore, k minus 1 can take any value 0, 1, 2 up to n minus 1. Okay. Therefore, if I sum over all possibilities of k in the allowed range, or equivalently of k minus 1, so the count is, the desired count is therefore summation n minus 1, k minus 1, k equal to 1 to n. If I give k minus 1 some name like L, then this is summation L equal to 0 to n minus 1, n minus 1 choose L, and this is nothing but the sum of the binomial coefficients. You know what it is? It is going to be 2 power n minus 1, everything, okay, it is something like 2 power n minus 1. So recall that we have shown an example for n equal to 4 and the count came to 8. But that is same as this 2 power 4 minus 1, that is 2 power 3, which is 8 as it should be. Okay, so this is a very important, interesting application of that theory, combinations with repetitions. Fine. Okay, so I think this is fine. I go to we will come to this question of unordered permutations later, somewhere later in this course. But ordered, not ordered, I mean ordered sums, they have a simple formula 2 power n minus 1. Okay, as I promised, we are going to have something on Catalan numbers. But just before that, I'll quickly recollect 2 standard results, which most of you must know, if not all of you. That is the binomial theorem and the multinomial theorem. So, this is something like this, x plus y whole power n is summation k equal to 0 to n, x power k, y power n minus k, n choose k. Or n choose k or n choose n minus k, they are basically the same thing, whatever way you want to view it. N choose n minus k, k equal to 0 to n, x power k, y power n minus k. This is standard binomial expansion. I am not going to the proof of this identity. You already know it. This is part of your higher secondary syllabus. And if you think, I do not know whether you already know this multinomial theorem. This is an extension of this. instead of 2 variables, I have something like k variables, and I look at the expansion of this when it is raised to power n. Then a similar formula holds, but it is much more complicated looking. So I now make a sum over all n1, n2, nk. These are non-negative integers and they add up to n. Now the coefficient is called the multinomial coefficient, written this way, xk power nk. So this multinomial coefficient n, n1, n2, nk, this is nothing but n factorial over n1 factorial, n2 factorial, nk factorial. Maybe you already know a proof for this, but it's not very difficult to see that if I just write it as x1 plus x2 plus xk, x1 plus x2 plus xk n times. So from each I am getting some xi, okay, and therefore eventually if I add these counts of x1 up, it will become n1, the number of times I get x2 is n2, and so on. Okay, so this is basically nothing but the total number of arrangements or permutations of the total of n objects containing n1 x1s, n2 x2s, n3 x3s, blah blah blah, nk xk. And you know this is the formula. Okay. Okay, good. So these two are important theorems. Just for the sake of completeness, I mention these two things. Now for the rest of today's lecture, I concentrate on Catalan numbers. Denoted popularly by C of n. This is not combination or choose, it's Catalan, named after Catalan. Okay. Suppose that you have something like an n by n grid. So you are starting from here, the 0, 0th point, and your task is to reach the top left corner, top right corner, n comma n. From bottom left corner, you want to go to n cross n comma n. And only movements that are allowed is either move right or move up. So for example, you can start here, 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 something like that. So choice of this R and U, and you should never go, of course, these are the only choices, you should not go outside this grid, because in that case you have to have some retrograde movement, left or down, something like that. Okay. So question is, the first question, which has nothing to do with Catalan numbers, but it's very relevant and related question. So how many paths, different paths are possible? From 0, 0, n, n, only these movements are allowed. Right means just go to the next point to the right. Up means go to the next point in the grid in the upward direction. So how many paths are possible? This is a simpler question to answer than Catalan numbers. So, a path is uniquely specified by a sequence of R's and U's. A path is any sequence of, how many R's should be there? 0, 0 to n, so you have to make n rightward steps, and from 0, 0 to n, this n implies that you have to make n upward steps. So a path is defined or specified completely by a sequence of n R's and n upward movements. So there is a total number of symbols 2n. Okay, the total of 2n R's and U's, out of which you can choose any n of this as R's. The remaining positions will be U's. And therefore, it turns out that out of 2n choices of R's and U's, you choose any n as R's. And each such choice gives you a path. And conversely, given any path, you can generate a sequence of n R's and n U's, and this construction is reversible. So that is the simple counting problem. From 2n choose n to this. In general, if I go from 0, 0 to m, n, I will have a total of m plus n movements, and I have to choose the positions of right movements in m positions, which is also the same as m plus n, n. Okay. I will soon use this result, the general m, n case. Okay. So the Catalan number asks for a very related question. Again, it asks how many paths are there, but now you look at this. This is the second line. So this is the line y equal to x. Okay. So C of n, the nth Catalan number, is equal to how many paths from 0, 0 to n, n that do not go to the top of the line. So these points are inaccessible. You can come here, but you cannot cross it. Now the question is how many paths are possible. One thing is for certain. First movement will have to be a right movement, otherwise you cross it in the first position itself. And the last movement must be an upward movement. You cannot come from here, somewhere from the top of this line y equal to x. But here you may have many possibilities like this. You have another possibility like start from here, 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 something like that. Okay. So now the counting problem is not so obvious. Okay. So I will tell you an application why we study Catalan numbers. But the definition, I believe, is clear, right? How many paths are there from 0, 0 to n, n that do not cross or go to the top of the line y equal to x? Okay. So this is 2n choose n, all possible paths, minus the count of the number of paths that goes the top of the line y equal to x. So these are invalid paths. This is the total count of paths, and if I subtract from this count the number of invalid paths, I will get my desired count, which is the Catalan number C of n, the nth Catalan number. So it suffices for computing this to compute the number of invalid paths. Okay. So I will count this. So let us consider paths that are invalid. Okay, so you are from 0, 0, you have this line ending at n, n. Since this is an invalid path, at some point it must go to, it will cross this line, right? It can be here, it can be here, it can be here. Of course, it cannot be here because you have reached destination at n, n. So let us say position k, this is the first time the path makes a non-allowed movement. So this line is k, k. At this point it goes to, it remains at k plus 1. Okay. So maybe here, there is no problem, but there is some point where this path crosses the y equal to x line going from below. And what are the possibilities for k? 0 in the first place itself, or 1 or 2, 3 or up to n minus 1. It cannot be n, because if you have reached destination, then there is no question of crossing. You cannot come back. No downward movement is allowed. Okay. Now I do a tricky construction. Now you have so far do something like this. Okay. Now this path has something right, up, up, whatever. Okay. So this is the original path P, an invalid path. So I construct a Q, another path. So I say that K is the first X value where the invalidity is manifested. It may be manifested again later, something like this. But this is the first thing. Okay. First position. So how many movements are here? 2K. K left, K right. Then you have another movement. Okay. So the first 2K plus 1 moves or movements of Q are the same as in P. Okay. So the Q exactly follows P up to this point. Okay. After that, this Q behaves little differently. It is just a flip of the path with respect to R and U. If P goes right, Q goes up. If P goes up, Q goes right. So up to this point, Q and P are the same. After this, U and R are just swapped. U becomes R, R becomes U. That is how I construct Q. Okay. So now let us see where Q ends up after these 2n moves, defined this way. First follow P up to this point, then flip U and R. Okay. So, where does Q end up? Okay. So now let us look at P. Up to this point, it has made K right movements and K plus 1 upward movements. But since P is a path from 0, 0 to n, n, it will have to make eventually n right movements and n up movements. So it has finished K of this. So remaining right movements must be n minus k. Right? K already done, n minus k, come up to n. Likewise, it has made k plus 1 upward movements. It will have to make eventually n movement. So this is the number of remaining upward moves. Okay. Now what Q does, it initially makes exactly k right movements and k plus 1 up movements like P. After that, it swaps R and U. So that means Q after this makes these many right movements and these many up movements. Right? Because R and U are swapped. Correct? So for Q, right movements are, number of right movements are, first K following the same as, what is that called, P, and then just the opposite, so n minus k minus 1. That is n minus 1. Okay. And how many up movements? Up to this it's same as in P, k plus 1. And then it uses the right movements for going up, n minus k. N plus 1. Okay. What is very interesting about this is that this n minus 1 and this n plus 1, these two quantities are independent of k. So whenever I convert an invalid path by following that construction, it will always end up at n minus 1, n plus 1. This is the point. So Q ends at n minus 1, comma, n plus 1. Somewhere here. This point. Okay. Conversely, if we take any path Q starting from 0, 0 to n minus 1, ending in n minus 1, n plus 1, then it is obvious that there must be some point where that path Q will cross this y equal to x line. It cannot otherwise go there, n minus 1, n plus 1. Right? Starting from 0, 0, our given path Q is going to n minus 1, n plus 1. So at some point of time, it will have to cross this line y equal to x. Maybe here, somewhere. Okay. And then if you reverse the construction, that is the first time it crosses this line, up to that point, it's m. And then reverse the R and U, then you will get an invalid path coming from 0, 0 to n, n. In other words, the construction of P to Q from an invalid path to a path from 0, 0 to n minus 1, n plus 1, this construction is reversible. Therefore, the number of invalid paths is exactly equal to total number of paths from 0, 0, n minus 1 to n plus 1. And these are unrestricted paths. Any path from 0, 0 to n minus 1, n plus 1 will give an invalid path from 0, 0 to n, n. There is no problem. And counting the number of paths from 0, 0 to n minus 1, n plus 1, that is easy using the generalized formula. So, number of invalid paths number of 0, 0 to n minus 1, n plus 1 paths. So, this is unrestricted. This turns out to this plus this, that is 2n, choose n minus 1 or n plus 1. Okay. Therefore, we have derived that this is the total number of all paths minus the total number of invalid paths, and it is easy to see this is a little bit of manipulation. 2n factorial n minus 1, n plus 1 minus n plus 1 to n choose n. This turns out to be 1 by n plus 1 to n choose n. So, this is the final formula. Okay. So, I once again write down clearly. Nth Catalan number is equal to 2n choose n divided by n plus 1. In particular, this proves that since this is an integer, this proves that 2n choose n, whatever that quantity is, for any value of n, this is divisible by n plus 1. Okay. So, this is what is called a combinatorial argument. This has to be an integer and it is written as a fraction like this by this. So, it has to be that 2n choose n is divisible by n plus 1. Okay. So, that's about derivation of Catalan numbers. We will come back to Catalan numbers once again, but I just give you a sample application of Catalan numbers. They have many combinatorial interpretations. So, I will talk about one such interpretation. Okay. Suppose you want to, you have a stack, initially empty. Okay. Empty initially. Then what will you do? You will push 1, push 2, push 3, push 4 and so on, push n in that sequence. And in between these pushes, you will make pop operations. Okay. So, push 1, push 2, push 3, push n. And you have pushed n elements. You have to pop out n elements, eventually letting the stack empty again. So, here you can make pop. That doesn't mean you have to make a pop. This is a position where you can make a pop. This is another pop position, allowed positions, and so on. Here also. Now, there is one restriction. You never make an attempt to pop from an empty stack. For example, if it is push 1 and you say pop 1, the stack becomes temporarily empty. Before pushing 2, you are not allowed to make another pop operations. So, n push, n pop, never from the empty stack. Okay. Now, you just print whatever you pop in the sequence. Okay. For example, if n is 4, push 1, push 2, pop, push 3, pop, pop, push 4, pop. So, first thing that is popped is 2, next one popped is 3, then 1, finally 4. So, this sequence 2, 3, 1, 4, whatever sequence you get by following these rules, let us call them stacky. So, 2, 3, 1, 4, 2, 3, 1, 4, this is a stacky sequence. So, for a general n, how many? The answer turns out to be exactly equal to C of n, the nth Catalan number. Why? Because you can think of each push. So, push are essentially right movements and pops are essentially up movements. And this extra condition, never pop from an empty stack, implies that if you have made k pushes at any point, you cannot make the k plus first pop at this point of time. In other words, you cannot cross that line y equal to x. Okay. So, this says never cross y equal to x. So, with this identification of pushes with right movements, pops with up movements along with this extra condition, it says that the count of stacky sequences for a general value of n is exactly equal to the nth Catalan number. Fine. So, we will see many other interpretations of Catalan numbers. I just mentioned maybe a couple of such things. So, suppose you want to multiply some matrices like this, n plus 1 of them. So, there is an order of multiplication. For example, you may first multiply A0 with A1, then A2 with A3, then this product and this product. Let's say that's 4. Another possibility is A0, A1, A2, A3, and so on. Right. So, the question is, in how many ways you can parenthesize the product explicitly in order to make the multiplication pattern explicit. Okay. This number again turns out to be C of n. Okay. So, this is another thing. Maybe we will prove it sometime as a tutorial exercise. And this is another thing which you are possibly not already familiar with. Structurally different binary trees on n nodes. So in your algorithm course, you will understand what is a binary tree and what is the structure of a binary tree. So this count, how many trees, structurally different binary trees are there on n nodes? This number is also equal to the nth Catalan number. And in fact, there are many combinatorial interpretations, many of which make enough sense in computer science of Catalan numbers. Okay, so we have seen three such things: Stacky, parenthesization, and binary tree counts. Okay, so let me stop. So let us call this the end of the section on elementary counting techniques. So I will come with a different topic in the next lecture, and my colleague, my co-teacher will also keep on posting his lectures on different topics. Okay, so let us stop and bye.